Hi, good evening. Today we are going to talk about conditional probability, and we'll talk about independent events and Bayes theorem, and we'll give an interpretation of the Bayes theorem as sort of an improvement upon an original hypothesis that you have about certain situations. Okay, so let's start with some real life examples on conditional probability. So the first example is a very familiar one. So you are standing at a bus stop and you're waiting for a bus to arrive. And so you have some preconceived notion about the times that the bus is likely to arrive. But then it starts raining. And so let's talk about some events. So let A be the event that the bus arrives on time. And let B be the event that it is raining. So by experience, you know that the events A and B are somehow related, and you would like to know the probability that the bus arrives on time, given that it is raining. So I will denote this probability as probability of the event A given B. Okay. So this is denoted as probability that the bus arrives on time, given that it is raining. Well, one would like to compare this to the probability of the bus arriving on time. And one would like to make some conclusions that maybe the probability of the bus arriving on time, given that it is raining, is maybe less than the probability that just the bus arrives on time, right? So, and one would like to know how to compute this probability. So this is our example number one. So we are talking about, in general, events that are related, and we want to compute the probability of an event A, given that event B has already occurred. Let's take another example. Example 2. So event A in this case is stock price of a company goes up. So of course, if you are trading in the stock market, you would like to know the correct timing of buying or selling stock. So you would like to know whether this particular company that you are looking at, its stock price goes up. Now, event B is the event that the company declares a profit. Again, our usual experience is that the probability that the stock price goes up, given that the company declares a profit, will be different if we don't know this additional information that a company has declared a profit. So again, in this case, we would like to compute the probability of the stock price going up, given that the company has declared a profit. Okay, so we had some original hypothesis. Let's call that probability of A is sort of an original hypothesis, right? We have some notion or belief that the stock price will go up. But now we have some additional information. So some evidence, information. And then we would like to compute this probability again, right? We are going to update our information by using the new evidence that we have got. That's example number 2. Let's take another example. Example number 3 is, let's say a crime was committed. So let A, and we want to know whether the crime was committed by a professional or an amateur. So let A be the event that the crime was done by a professional, and B be the event that so how would we know that the crime was committed by a professional? We would like to study the type of evidence that was uh, given by the professional. So let's say let B be the event that the type of evidence, let some type of evidence which is we are assuming over here that professionals leaves a particular kind of evidence. Okay, so again we would like to know probability of A given B. Okay, so having known the new evidence, what is the probability of the crime being committed by a professional? Okay, and a final example that I have over here is let A be the event that let's say I am wearing a red shirt. And let B be the event that it is raining. Then it is somewhat obvious that me wearing a red shirt shouldn't have anything to do with the fact that it is raining. So in this case, the probability of me wearing a red t-shirt, given that it is raining, or the occurrence of event B shouldn't have anything to do with the probability of event A. So in this case, we should have something like this, right? The probability of A doesn't get affected by the occurrence of event B, in which case we will call these events A and B. A and B are unrelated, or they are independent events. Okay, so with these examples that we have given, we would like to then go on and try to define how to compute this particular probability. Okay, so let's see how we can compute that. All right. So so let's look at a particular sample space. So let's say we have a particular sample space omega. I'm drawing it over here. And let's draw our event B. So within omega, we have this event B. And let's draw our event A. And our goal is to compute probability of A given B. Okay. So the idea over here is since the event B has already occurred, we want to look at the reduced sample space. So reduced sample space is not the entire sample space, but since B has already occurred, we just look at all the events that are in B. So basically this part. Okay. So we are not looking at any of these events. We are not concerned about these events because the event B has already occurred. And now we are interested in computing the probability of A. So since the part of A that lies in B is just this part, right? So it's this part. So one way to compute the probability of A given B is just look at the number of events in A that are also in B. So let me call that, and we are assuming that this is an equiprobable space, which means each and every event is equally likely. So this is our favorable outcomes because we are looking at the probability of event A occurring, given that B has already occurred. So looking at the reduced sample space, we get the favorable outcomes as, and then the total elements in the sample space is just B. Now, if I multiply and divide both numerator and denominator by the number of elements in the sample space, I get so this is my total number of elements in the sample space, n of omega. So I'm dividing the numerator and denominator by the total number of elements. And then you see that this is equal to the numerator over here. This part is probability of A intersection B. And the denominator over here is just probability of B. Right? So then this will be our definition of, this will take as our definition of probability of A given B. Okay, so this is the way to compute the probability of A given the event B has occurred. Okay, its definition is probability of A intersection B divided by probability of B. Now, we said earlier that if two events A and B are unrelated, then probability of A given B is equal to, so this is only if A and B are independent, right? So this is if A and B are independent, right? So if I substitute in the previous equation, I can substitute A given B as probability of A. So we get probability of A is equal to probability of A intersection B over probability of B. And therefore, probability of A intersection B is equal to probability of A into probability of B. So this will be our definition of independent events. So this is our familiar definition, which many of you might have studied. So definition is that two events A and B are independent if probability of A intersection B is equal to probability of A times probability of B. Okay, so this we will take as our definition of independence.